amplitudes and correlators in planar unequal force regimes.
Thank you very much. I'd like to thank the organisers for this very nice conference and for the opportunity to speak here. Sounds very loud and echoey. Does it sound all right to you guys? Okay. So the talk here is on 4-point amplitudes and 4-point correlators in planar n equals 4 young males. It's based on some work we did at the end of last year and some current work with Jake Borjali and Viet Tran, who's a student of mine in Durham. Okay, so I'll begin by, I won't introduce 4-point amplitudes in n equals 4 super young males, because, well, first of all, Lance gave a very nice talk motivating n equals 4 super young males, and you all know about amplitudes. Although, unfortunately, he told us that 4-point amplitudes are trivial in n equals 4 super young males, which rather kills this talk a bit, but so it's the log of the amplitude analytically is given by the BDS ansatz, but the integrand of the 4-point amplitude has a lot of nice structure, which I'll be discussing here. So what I will spend some time talking about is the correlation function, and I'll explain how that gives the amplitude at the integrand level. And then I'll talk about some results that we've got up to 9 loops fully and 10 loops partially for both of these quantities. I'll spend some time going over the method in some detail. It's sort of bootstrappy in the sense of you obtain it by symmetries, analytic properties, and then various methods that we have for, so these, there's a hidden symmetry as well. These enable you to vastly reduce the basis of objects that you need to consider. So up to 3 loops, there's only one object. But then at higher loops, you still have a number of coefficients that need fixing, and I'll discuss basically 2 different methods we have for fixing these. So one method we used at A loops, and now we're using a different method at 2 loops, which are above 8 loops, at 9 loops, which I'll discuss. I'll then briefly talk about higher point amplitudes, because although this is to do the 4-point correlation function, you can actually get information about higher point amplitudes from the 4-point correlation function, and then I will conclude. Okay, so very briefly then, correlators n equals 4 super young males. So I'm going to be talking about this 4-point function. Remember to use this. Of 4 gauge invariant operators, and the gauge invariant operator is obtained by simply taking one of the 6 scalars of n equals 4 super young males. Any one will do. Squaring it and taking the trace. That gives you an operator. You can get the 4-point function of 4 of these operators, so inserted in space-time, position space, x1, x2, x3, x4, and take its expectation value. Then because of the nice n equals 4 superconformal symmetry, so this particular component correlator is related to any other correlator of any other operator which is related by supersymmetry to this operator. Just like MHV amplitudes, if I consider a particular gluon amplitude, I get for free all amplitudes related to that gluon amplitude. Okay, and it's called the stress energy supermultiplet because the stress energy tensor is related by a supersymmetry to this guy. So this is the simplest operator you can consider in the theory. Has lots of nice properties. It's related to supergravity by ADS-CFT. It's related to supergravity just on ADS-5. It's protected from, it doesn't have any enormous dimension. It's a protected quantity of BPS, and so on and so forth. For that reason, the 2- and 3-point functions of these guys are trivial, and the 4-point function is the first non-trivial object. Okay, so there's lots of independent, by independent I mean independent of the amplitude, which I'll talk about in a second. There's also independent reasons for being interested in this object. You know, in particular, there's this nice recent work by Ben and Amit, who are here, and collaborators, and lots of other people working out three-point functions. And these can all be, well, not all of them, but many of them can be obtained from this particular correlation function. Okay, but the thing that's going to be of most interest to people here is the relation to scattering amplitudes. So the point here is that in the planar limit, if I take this correlation function and divide it by its tree-level version, and then I take this polygonal light limit, which we're familiar with from other contexts, in particular the Wilson loop, I guess. Then you get the square of the amplitude. So all the quantities here are the full amplitude, so an expansion in the coupling. Full perturbative correlation function is equal to the full perturbative amplitude squared. Okay, and then so these are position variables, and they become then the region momenta, the amplitude written in terms of region momenta, which we're familiar with. So this quantity is infrared divergent, and we can use, for example, dim reg to deal with that. However, the integrand of this object is a perfectly nice rational function. And it's the integrand, at the integrand level that I'm going to be discussing this. So similarly on this side, this correlation function, by the way, is a completely finite quantity as long as your x's are at general positions. It's completely finite, but when I go to this limit, it becomes divergent. So both quantities are divergent, but at the integrand level, then both quantities are perfectly well defined, and I'm going to be looking at this at the integrand level. Okay, so I'm going to give an increasing amount of detail about how I'm going to compute these things. So first of all, they're integrands, so they're rational functions, nice simple objects. There's just a lot of variables. Superconformal symmetry enables us to write it in terms of just one quantity of just of the x's. Analytic properties tell us I only have single poles, much like amplitudes, I only have single poles. Planarity we use, as we'll see, and then a very powerful symmetry which we call hidden symmetry. And then there's these two methods that I mentioned on the introduction, both of which can be summarized by this statement. Okay, so first of all, the superconformal symmetry. So a bit like MHV amplitude, you can factor out a universal piece. So this is for all loops. This is a correlation function at L loops. There's a universal factor. It's not actually a tree-level correlation function in this case, as it would be for an amplitude, but nevertheless it's a universal factor multiplied by a quantity. And this is the quantity that I'll be looking at. It's just called F. So this is, it depends on your four external positions. And then because this is an L loop object, it has L integration variables. And I label these rather suggestively x5 up to x4 plus L. And then the hidden symmetry, which is a very non-trivial consequence of crossing symmetry together with superconformal symmetry and the structure, gives us this this hidden 4 plus L permutation symmetry. So in particular, it's completely symmetric, interchanging all variables, 4 external ones, and the integration variables all get mixed together, and it's completely symmetric under this. Okay, so we can use these facts together with the fact that there are no double poles to simply try and write down rational functions that possess all of these properties. So conformal, well, the Remps and translation symmetry tells me it's just a function of xij squared. Conformal symmetry tells me that they have certain homogeneity properties in the various variables. So it's got weight 4 in each variable. And then you can discuss this graphically. So in the usual way that you would expect from Feynman diagrams, I have an edge is 1 over xij squared. And then the problem simply becomes one of writing down all graphs that have valency 4 in 4 plus L points. So this is on all points, including the external ones. There's now no real distinction between external and internal points. So this is naively, there's this word naively here, so you can also have numerator lines, and they become increasingly important as you go higher up in loops. So that means you really look at degree greater than or equal to 4, such that you can attach numerator lines which reduce the degree to 4. Okay, so the easiest way to look at this is to see some examples. So the one loop example is the only thing I can write down that has conformal weight 4 is just the list of all possible xij squareds. It's the only thing you can write down. Graphically, then, I've got all possible edges between 5 points, and then this is the graph. So 2 loops. It turns out that the only thing you can write down is this guy. So it's easiest to write down the missing edges rather than write down the edges that are there. So this is all edges. And then the missing edges are x1 2 squared, x3 4 squared, x5 6 squared. Here's the corresponding graph, so that might be 1 2 squared, that edge is missing, that edge is missing, and that edge is missing. And then you sum over all permutations, so I don't need to label it because I'm summing over all possible labelings. And this is actually an octahedron. If you write this in a 3-dimensional way, this is an octahedron. So finally, even at 3 loops, in fact there are 4 different graphs you could write down at 3 loops, but there's only one that's planar. And it turns out that we only need to write down planar graphs. And this is the expression, but it's all summarized by this single graph. And here you see there's this x1 2 to the 4th, which really means x1 2 squared because I'm cancelling one of the denominators. But there is a remaining x1 2 squared. That's what I mean by a numerator line. So this is the graph. There's a hidden numerator line going between these blue dots. You could draw that as a dashed line. And you see this is a degree 5 vertex, and the numerator reduces it down to a degree 4 vertex. Okay, so later on I'm going to be showing you some sort of pictures. So this, it's useful to see this in a 3-dimensional version. So this guy, that you can see there's a sort of a pentagon around here, and a north and a south pole, and there's the 3-dimensional version of it, sort of rotating around the equator there. Okay. So then you go to higher loops, 4 and 5 loops. The basis is still pretty small. There are only 3 objects you can write down at 4 loops. There are only 7 objects at 5 loops. I've put in these pluses and minuses, but we don't know what they are yet. I haven't told you how to compute those. That's what I'll tell you at the moment. At the moment, we just know that it's a coefficient times this plus a coefficient times this plus a coefficient times this. So these, I know the 5 loop guy up to 7 unfixed coefficients, just using the arguments I've given you so far. Okay, so this is for the correlation function. How do I go to the amplitude? Well, algebraically, I just do this limit, wherever it was. I just take that limit. But you can see what this means graphically. So I'm taking a polygonal limit. Now the only terms which are going to survive, or the leading terms, are ones where I have a square in that limit. I have 1, 2, 3, 4 connected by a square. In other words, I have all of these propagators. They're clearly going to be the leading terms. Anything that doesn't have the 4 propagators is subleading. So then this becomes the question of finding 4 cycles, inequivalent 4 cycles within my F graph. Now this gives me the amplitude squared. The amplitude squared, if I write it out, so it's the expansion of the amplitude squared. So for example, I'm giving you a 3-loop case here. The amplitude squared gives me the 3-loop amplitude plus 2-loop times 1-loop. And you can see all of these things coming out graphically from this F graph. So here is the same F graph, but I've sort of coloured in a 4 cycle. So there's a 4 cycle from there to there to there to there, and I've coloured that in red. And now if you ignore the red bits and just look at the black bits, you'll see, with a little bit of imagination, that the black graph that's remaining is precisely this graph here, which is the dual graph of the 3-loop ladder. But there's another way of finding a 4 cycle on the edge of this F graph, an equivalent one, which is given here. So there's the 4 cycle, 1, 2, 3, 4. Again, I've coloured it differently, and then the remaining black stuff gives you, again, if you unwrap it and fold it out flat, it gives you this graph here, which is the tennis court diagram. So these 2 graphs you recognise as the graphs of the 3-loop amplitude. And then finally, there's only one other type of 4 cycle inside this 3-loop F graph. And this is a 4 cycle which somehow splits it into 2. It goes through the middle of the F graph. So it goes 1, 2, 3, 4. And now you see the F graph is split into 2 pieces. This sort of piece here is a box, and this piece underneath it unwraps to become the 2-loop ladder. Okay, so you see all these ingredients coming out. And this actually leads to a nice way of obtaining higher loop graphs from low loop graphs. It was discovered much earlier in the context of amplitudes. But here it's derived basically from this duality. And the point can be sort of seen already here. So the limit of the correlator, sorry, that should say limit of the correlator, it gives me the amplitude squared, which contains lots of terms. In particular, it always contains a term with the L minus 1 loop amplitude times the 1 loop amplitude. And this is what we saw here, in fact, with this graph. But you see, the 1 loop amplitude, let me try and get this so the 1 loop amplitude is actually a pyramid. So this 1 loop amplitude you can think of as a pyramid that you stuck onto a previous graph, the L minus 1 loop graph. And in fact that gives you a way of sort of adding pyramids to graphs to generate higher loop graphs. And the point is, this rule tells you that the coefficient in front of these always has to be the same as the coefficient of the guy that it started with. That actually, if you rewrite it in terms of amplitude in momentum language, is the run rule. Okay, so here, this is my 3-loop F graph. Let's just go back to my list. So that was this one, so this has coefficient 1. This tells me that these 2 guys have coefficient 1 as well. It doesn't see this guy, the run rule doesn't see this guy with the minus sign. So here, those 2 graphs are actually the same as the other ones. Okay, very good. So I've shown you how to generate these graphs, and I've shown you how to get some coefficients using the run rule, but not all of the coefficients. So we need something else to fix the coefficients. And these guys found a very nice way of fixing coefficients for amplitudes by examining divergences. The argument is quite simple. It says that the log of the amplitude, as we know from well, for lots of reasons, in particular from the BDS. The log of the amplitude only has a 1 over epsilon squared divergence, whereas the amplitude itself has a 1 over epsilon to the 2L divergence. So you can examine where the divergences come from, and look at the log of the amplitude at the level of the integrand, and this puts constraints. I'll show this in a bit more detail in a moment, in a different, slightly different context. But this means there's a zero as one of the integration variables becomes collinear with one of the external momenta. And this criterion is enough to fix all the coefficients. However, because I'll put 8 loops, 9 loops, the thing is getting quite big, as you can imagine. You want an efficient method as possible. So this is the most powerful method, but then there's a very simple and it's a very efficient to implement method. And it simply states that if I take the L plus 1 loop F graph, so I have my basis of F graphs with coefficients that I want to fix. I take that and I shrink all triangles. So this is new, by the way. I shrink all triangles. Then I should get the same result as if I take all L loops, which presumably I've fixed those coefficients using a previous iteration, and I shrink all the edges. Okay, so first I'll show you an example of that and fix that -1 at 4 loops using it, and then I'll derive it. So here's an example of this working at 3 to 4 loops. So remember, I want to take so here I want to take the 3 loop guy and shrink all edges. And the answer is supposed to be equal to what I get by taking the 4 loop guy and shrinking all triangles. Well, you probably need a bit of imagination to really see this, but hopefully you can believe that if I shrink this edge here, then I get this graph. It's now, because I've shrunk an edge, there's 2 lines going from the same vertices in 2 different ways, but that's fine, it's still a graph. There's an inequivalent edge. There's only 2 inequivalent edges on this nice symmetric line. There's the ones going from the poles to the equator, and there's the ones around the equator. If I shrink this edge around the equator, then this gives me this graph. And in fact, you can now take the 3 4 loop graphs that I had. So they're drawn in 3 dimensions like this. This one and this one are the same graph, but with inequivalent triangles. I shrink those triangles, and in fact you get G2, which is what I'm calling this reduced graph. You get the same graph. This guy, I reduce this triangle, and I get G1. And now there's 3 other graphs, so they give me, that one gives me G1 if I shrink a triangle, that one also gives me G1 if I shrink a triangle. So in this way I get an equation. If you buy this this criterion, this gives me an equation. It tells me that the edge shrinks. These are fixed. This has coefficient 1. This is a 3 loop guy. It has a coefficient 1. So this gives me G1 plus G2. These guys have unfixed coefficients, B1, B2, B3. So it gives me this simple equation. And this has the solution that B1 is equal to 1 because G2 only appears there. And then B2 plus B3 is equal to 0. Okay, so let's go back to the 4 loop guy and see what we found. So we found that the coefficient of this was 1, and the coefficient of this is equal to the negative of the coefficient of that. So that's without using the rung rule. But of course we know from the rung rule already that the coefficient of this is 1. And therefore that fixes all 3 of these coefficients. Okay, so in that simple example, you see that this criterion fixes all the coefficients for you. Okay, so Maybe I'll quickly try and convince you about where this criterion comes from. So it has a very simple origin, actually, to this divergence criterion. But it's more correlation function oriented. So first of all, it's true that the log of the correlation function only has a single log divergence in the coincidence limit when x2 goes to x1. And that comes about because of, well, it's to do with an OP limit and the Kanishi operator and its anomalous dimension. There's a single operator with a single anomalous dimension, so there's an exponential of a log here, and that goes down for the correlation function. So the correlation function itself at L loops would have log to the L x12 squared divergence. But the log of the correlation function only has a single log divergence, just as we saw for infrared singularities of the amplitude. So again, you can examine this at the level of the integrand, just as these guys did for the infrared divergences. And here it says that the divergence comes from when one of the loop integration variables goes to x2 and x1, which are also going to each other. And you're supposed to get a 0 in that limit. Okay, so it's a 0 times a divergence, but you can understand that you can separate these out quite cleanly in the integrand level. Okay, so far it's exactly the same story as for the soft collinear divergence. Now you can reinterpret this, and indeed a similar reinterpretation was done for the collinear case by Golden and Mark Spradlin. You can reinterpret it as saying that in this limit, the L loop correlator becomes the L-1 loop correlator times the divergence. So actually, it's not so easy to see why this is the case, but if you rewrite the log in this way, which you can do, so this is the log of the correlator. I mean, you can write the same formula for an amplitude. The log of the correlator is given by the correlator minus the one loop times L-1 loop, together with lots of things which contain logs of lower loop correlators. And then you can prove this statement by induction. Okay, anyway, then finally this statement can be reinterpreted at the F-graph level as a shrinking triangle. So you can see here I'm sending 3 points together, and over on this side at L loops, and over on this side I'm sending 2 points together. And that's the origin of the triangle shrink is becoming the edge shrink. Okay, so I probably already mentioned this. So the soft collinear divergence thing is more powerful, but it gets more complicated to implement. And this guy is obviously very conceptually appealing. I'm just shrinking triangles and shrinking edges at the level of the graphs, but it's not quite as powerful as we've already seen at for loops. We needed the run rule as well. But when you're getting to 8 loops and so on, this is the way to proceed. Okay, so this summary of what we've achieved so far. So there are sort of two different groups getting up to 7 loops. Actually, Henrik and Krasko also got the 6 loop amplitude using other approaches. Anyway, so there's the soft collinear divergence approach. We did the correlator at 7 loops. We mainly used also the soft collinear divergence approach, in fact. But we could have done it using the 7 loop approach. The 8 loop result that we did at the end of last year, that was again using the soft collinear divergence method. And now we're going beyond 8 loops, and we're going towards this triangle shrink method. Now, as I already said, it's not quite as powerful, so at 8 loops, if you do it, it leaves 22 free coefficients. So now there's 2 ways to proceed. You can get another criterion for fixing coefficients, which we can do, and I'll mention very briefly at the end. Or what you can do is you can just keep going. Leave your 22 free coefficients there, and try and do the shrink at higher loops, 9 and 10 loops, but with free coefficients still at lower loops. And this triangle shrink thing actually fixes these lower loop free coefficients by consistency. You just leave them in there, leave them in your equations, but the equations fix the lower loop ones as well as some of the higher loop ones. Okay, so we've been able to completely fix the 9 loop result then. And the 10 loop one, we've got the equations from here, and we need to solve them. But there's a lot of them. Okay, well here are the number of coefficients. So as you saw, it starts off very slow. That was the very nice feature. So at 4 loops we only had 3 coefficients, but it still gets big as you get to 10 loops. These are, by the way, these are the starting plane graphs where you look for all graphs of degree greater than or equal to 4. And you see that to begin with, there are fewer F graphs because not all of these graphs can be uplifted to F graphs. But then later on, that's still the case, but now you can put the numerators on in so many different ways, you end up getting more F graphs than you do plane graphs. And lots of these are zeros as well, so there's still some inefficiency here. We really need to understand better which guys are 0. But anyway, compared to the number of amplitude graphs, we're a lot better off, as you can see. And if we had another column here for the correlator integrands, then that would be even bigger again. Okay, well I haven't got too long. Let me just try and point out a few features of the results that we found. So the first new feature that appears at 8 loops are the occurrence of these finite integrals. This is for the amplitude now. This is all talking about the amplitude, and these diagrams are written in momentum space. So you see this particular graph here. Now it contains within it this 2-loop double box, completely massive, which is known by the work of Kasper Larsen and Simon Perrin-Duot to be sort of going beyond polylogs into elliptical functions. So there's an integral which contains within it this integral. So of course we don't know anything about this thing, but you suspect that it should go beyond polylogs. Okay, so then there's a little kind of speculation. You can say, are there non-polylog contributions to the 4-point amplitude? So this would still be perfectly consistent with BDS. These are just numbers, by the way. Sorry, I should emphasize that. These are numbers. They're finite, but their amplitude and they're conforming invariant amplitude. So the only thing you can have is a number. So there's some sort of numbers. So this would actually contradict the results of these people who showed that you only get D log integrands for all MHV and NMHV amplitudes, and therefore, well, I don't think this is a direct statement, but it's strongly suggestive that you only get pure polylogs. Of course, there's no contradiction here because I've got 4 of these guys. Well, first of all, I don't actually know that there's anything non-polylog here. But in any case, there's 4 of them, so the non-polylogness can cancel amongst the 4 of them. Okay, but it's interesting that we see them in the result. And then there's a sort of, it's almost the opposite result. So the amplitude is divergent, but we see finite graphs. The correlator, on the other hand, is finite, but we see divergent integrals for the correlator. The first time. These ones have to cancel, and in fact they do, you can check that they cancel, but they appear in the ansatz. These were things that we didn't see at lower loops, and it was used as a reason why zeros appeared for the amplitude at lower loops, in fact. In fact, you can analyse the different types of divergences. So here, this is again written in momentum notation, but if you imagine the dual picture, it would be a pentagon. There'd be a sort of a pentagon with a dot in the middle of this guy. So these guys never appear, but these guys can appear, these divergences. And there's a sort of a correlatory reason why these guys can't appear. Again, coming from the run rule, it would have to come from a lower loop amplitude that was non-planar, and anything of this form. Okay, the other new features are new coefficients. So as you saw, I gave you all the coefficients up to 5 loops, and they were all plus or minus 1s. In fact, up to 3 loops it was just plus 1s. At 4 loops we saw a minus 1 for the first time. At 5 loops, at 6 loops, then we saw a plus 2 for the first time, which was sort of intriguing, intrigued me and various other people for a while. And then, of course, we wondered what we would see. At 7 loops, we don't see any new coefficients, just a single plus 2 again. That came from the wrong rule on that. At 8 loops, then we see a few more coefficients. In particular, we see some half-integer coefficients. And then there's this one graph that appears that has a coefficient of a minus 5. And these graphs are sort of the same type of graph. The new coefficients always come with a certain type of graph. So this minus 1, this 2, this 5. So they all come, and I was looking at these are called anti-prism graphs. So there's a 4-sided anti-prism graph. So again, it's got a square on the top and a square on the bottom. I don't know how easy it is to see that, but and triangles in between. That was the minus 1. The plus 2 is has a pentagon on the top and a pentagon on the bottom, and this minus 5 at 8 loops is a hexagon, 6-sided antiprism. Actually, if you prefer, if you don't like the 3D things, then you draw it flat, it's given by the Nordita logo. So at 10 loops, as I said, we've got the equations, we haven't fixed all of them yet, but nevertheless you can see some features, and again this pattern seems to be continuing. So there's a new coefficient of plus 14, and it's given by this 7-sided version of the antiprism. That's at 10 loops. Okay, thank you. I'm nearly there. Okay, so I want to emphasize something right at the end here, which hasn't been emphasized enough, I don't think, which is that this 4-point correlator, in fact, can give higher point amplitudes, or at least it can give information about higher point amplitudes. So the first thing is that if instead of taking a 4-point light-light limit, if I take a 5-point light-light limit, and I get the combination of the 5-point amplitude, 5-point MHV times the 5-point MHV bar amplitude. So this is a nice quantity because the correlation function is a nice quantity, meaning it's just a function of xij squared. Whereas M5 and M5 bar by themselves have an epsilon, have a parity odd piece, and this quantity doesn't. And this continues, so if I do a 6-point light-light limit, then I get MHV 6-point times MHV bar 6-point plus the next MHV squared. And this again is if you took all these individual guys, there's R invariants in here. I have to multiply them together, square them, and out pops a nice quantity. And then this continues. This is general statement. You get this sum of n to the k MHV and n to the, well, this is n to the k MHV bar, basically. And we can just read that off. We have the correlation function. You can just take this light limit and read off these quantities. At 5 points, you can actually do more. You can disentangle the 5-point amplitude from this quantity, and that's because the topologies cleanly separate out, much as we saw at 4 point when I analysed the light limit as the cycles inside the graph and the cycles on the edge. And well, I won't go into details here, but you can use this to actually put more constraints on the correlation function. So much like the rung rule, I can try and do a similar thing that I did for the rung rule from 4 points at 5 points. It gets more complicated because I'm multiplying parity odd things together, and I get a whole slew of stuff coming out, including non-planar diagrams. But nevertheless, you can distill out from this a nice simple criterion which can be used to fix, for example, at 8 loops it can fix all the 22 coefficients without having to resort to going to higher loops, and so on at 9 loops. Okay, good. Well, I'm basically out of time, so I mean, the main thing for me, continuing directly from here, is there seems to be, it's clear that there's a lot of structure that we're not understanding here, especially this 5-point stuff. What would be lovely would be to have a graph generating algorithm, so I don't have to spit out all F graphs and then fix the coefficients. But much like the rung rule, I would have an algorithm that would spit out the graph and the coefficient. This is just dreaming. I have no idea if we can get something like this, but has to be consistent, of course, with all the procedures that we have so far. Okay, we need to find integrals. Of course, these are only known to 3 loops, so we need to look at 4 loops. There's this speculation about these guys, but that looks quite a long way away from what people can do, I think. And then you can speculate about amplitude-hedrons and correlahedrons and things. I'll leave it there. Thank you.
Questions?
I have one comment and one question. So the comment is that this 8-loop integral that you suspect would be elliptic.
Right.
But I think that it's not even clear if it is not at York. Yeah, this 2-loop massive double box is not at York, but that's not a proof that once you embed it into the 8-loop diagram. There is actually some lower loop example when similar thing happened, and it's at York.
Oh, okay.
If it then integrates to polylog or elliptic, I don't know.
Right.
Now the question is if, because some of the method with UU was using the fact that the lock of the amplitude has a nice behavior in the IR. Is there any understanding what the lock means at the level of correlator directly? Because in order to use this procedure, you have to subtract all the lower loop products and so on. But if there is some understanding what the lock of the amplitude directly means at the level of correlator.
Well, first of all, that's not, the last statement is not true. That's precisely the point. I only have to do this triangle shrink and edge shrink. I reinterpret it, so I don't have to subtract all these lower contributions. The interpretation, I mean, the divergence is the Canesian anomalous dimension. So here, this is the divergence. I mean, the divergence is log x1 squared times the Canesian anomalous dimension. Much like you get gamma cusp for the amplitude.
Right, I mean what the correlator means at the level of these graphs. What the lock of the amplitude means at the level of these graphs.
Oh, I see. Right. No, not really. I mean, of course, the square of the amplitude for me is a very nice object. It has this hidden symmetry. But the log of the amplitude or the log of the correlator, I mean, you can work it out. But I mean, it is what it is. You take g2 minus a half g1 squared. I don't have any particular nice thing to say about it.
This is just a comment. You mentioned it in passing, but the power of the soft closing or bootstrap method, it is a very powerful method. It has proven itself, but only with the strength of the correlator, though with this hidden symmetry, because it loops these finite things.
Oh yeah, I think I wrote it, but I didn't mention it. Yeah,
you did mention it, but I thought you were a little over generous about the strength of it, at least as originally formed.
Yeah, no, that's true. These finite integrals, of course, are finite, and therefore cannot ever be detected by that method, which is detecting divergence.
More questions? No? Now let's thank Paul and all the speakers.